The next example that we're going to use for motivating calculus is what's called the tangent problem. So if you are given the graph of some function, f of x, can you find the slope of the tangent line at some point where x is equal to a? So this will be the x-axis, and right there is a, and I would like to figure out the slope of the tangent line. And so usually everybody recognizes the tangent line. Oh, it's a line that touches the graph just once. But it's not something like that, because that's a line that touches once. Instead, what it is it's something like this. Now, everybody said, oh yeah, you'll nod your head and say, yeah, but we don't really have a better reason as to why it's that and not the one I drew before. So the reason we will save and talk about a little bit later. Now, I'm hoping at some point in your life you've talked about slope. Slope, they usually like to give the letter M. It's a French word. It's monter for climbing. And everybody remembers it as rise over run. You've got some formulas. The change in height over the change in width. y2 minus y1. x2 minus x1. If I only tell you a single point on the graph, if you know one point, all you know are one set of coordinates, a and f of a. How am I going to find the slope if I only have one point? Now, you might try to be idealistic about it and do the same thing we did with velocity. You just say, well, maybe you can just plug in the same value twice for y and then the same value for x twice, and maybe that'll work. And of course, you get back to this 0 over 0 nonsense. What we have to do is try something else. And so we need a new idea. Well, if you need 2 points to find the slope, invent another point. So we're going to use a point on the function that is near x equals a. And that's vague. How close? What do you mean by near? So the tangent is this line right here. This is the one we're interested in. The information here is a single point, a and f of a, and we can't figure out the slope. We don't have enough information right now to calculate that. So instead, what we're going to do is pick another point that's kind of close. I'll just call it x, and its height then is f of x. What I'm going to do is take that point and then draw a line between them. And so in this case, I can approximate the slope. The slope here is going to be y2 minus y1, so I'll say f of x minus f of a divided by x2 minus x1, so x minus a. That slope is for something that we call a secant line. Now, a secant line is a line that goes through the graph twice, 3 times, whatever it is, but we don't want that. We want to move this point x and f of x closer to the point that I do know. Why? Why do you want to do that? Because the red line doesn't match the blue line. You'll have this green line. If I move the point closer, the green one doesn't match the blue one either, but it looks better. The closer I make these points, it kind of looks like the better and better the secant line starts to imitate the other one. So as the spacing, we're going to call it h, so we'll say that this space in between here is h. As that spacing goes closer to 0, the secant lines seem to get closer to tangent lines. That should feel really familiar. It seems like we've got this whole limit idea going on again. That's exactly what the mathematicians way in the beginning started to notice. It's this limit process again. This is the same idea we used for that velocity problem. In terms of math symbols, the tangent slope is going to be the limit as x approaches a of the secant slope. So the secant slope, we will have f of x minus f of a, x minus a. As x gets closer to a, f of x gets closer to f of a. They never equal each other, because if they did, we get back to that 0 over 0 business. And so mathematicians said, this is the way that we are going to talk about slope if we only ever know one point on the graph. And it's the same limit process that we did from that other problem. We will talk more about the limit process in class.